Good afternoon. My name is Laxmi Rao, and I'm a director at IDEA, the International District Energy Association, and I'm very pleased to welcome you all to this webinar today. But first, I would like to apologize on behalf of IDEA and Johnson Controls for this delay this afternoon getting started. I see 203 attendees, so it looks like most of you are on. We welcome you to this webinar, and we'd like your participation and questions. Today's topic is designing a chiller plant to get the most efficiency, and we have with us two experts, Roy Hubbard and Bill Stewart from Johnson Controls, who will share insights on this topic today. Before I introduce them, I would like to go over some housekeeping items. We did start late, but the webinar is going to go on for about an hour and 30 minutes. The panelists, please silence or shut off your cell phones. We're going to take questions at the end of the presentation, but to all attendees, please type in any questions that come up as you listen to the content in the bottom right corner of the screen where it shows there's a Q&A box that you can type in your question. I will be collecting them throughout the presentation and hand them off to the presenters to be answered. We'll try to get to most of the questions, but if some remain, then we will have responses provided by Jill Woltkamp after the webinar. If you have just dialed in with the audio and cannot use the Q&A box, please send your questions to Jill at the email address shown here, jill.h.woltkamp@jci.com. If you continue to have questions about the webinar and issues with connections, please chat privately to Cheryl. We ask that at the end of the webinar you please complete a survey. It will provide valuable insights into how we did and how valuable the content was. And lastly, we are recording this webinar, so you will see the recording. You'll get the recording, the audio, and the presentation at the IDEA website at www.districtenergy.org. This, as I said, is the second in a series of 3 webinars, so it will be more meaningful if you watched the first one, which is about variable speed drives in central plants with multiple chillers. So the theme of this series of webinars is Select, Design, and Optimize. And August 16th was the first webinar, as I mentioned. Today we're going to talk about designing a chiller plant to be most efficient. And heads up, we will have the third in the series on December 6th on defining and implementing chiller plant optimization. With that, I'd like to introduce the two speakers for today, who between them have over 60 years of experience. For over 3 decades, Roy Hubbard has been part of Johnson Controls' building efficiency business. In his current position, Roy is responsible for bringing the company's water chiller solutions to the global market and for advocating advanced practices in energy-efficient chiller plant design. He's a noted expert on energy and energy calculations and has authored numerous articles on energy topics. Based in York, Pennsylvania, Roy travels extensively to present customer seminars and speak before industry professional groups. He received his Bachelor of Science degree in Engineering from the U.S. Military Academy at West Point in 1974 and completed 5 years of military service before joining Johnson Controls, formerly York. Also with us today is Bill Stewart, who has over 30 years of experience and has been part of the industrial and commercial refrigeration and large tonnage special drive chiller businesses. In his current position, he's located in York, Pennsylvania, and is responsible for application and technical support for a wide range of global applications. Bill has worked on many applications around the world, including U.S. federal government sites, universities, municipal authorities, private entities, and international sites. Bill received his Bachelor of Science degree in Mechanical Engineering from Ohio State University in 1977 and has a professional engineer license in several states. He's also a certified energy manager. So with that, I'm going to turn over the webinar to Roy Hubbard, who will go through the agenda and the rest of the presentation.
Good morning, all, or afternoon, or evening, or night, whatever time zone you happen to be in. Our agenda for today is to first review the 5 VSD myths from last time. That'll be very quick. Then to look at 3 new myths that are centered more around the central plant, whereas the first 5 were settled really more around the chillers. Now we're going to step into the pumps and towers. Then we'll summarize and provide an opportunity for some Q&A. So let's review these 5 quick myths that were in a chiller plant. The 5 myths from last time, if you were at that webinar in August. Myth number 1 is, in a central plant, you should run the fewest number of constant speed chillers as heavily loaded as possible. Generally speaking, this appears to be correct, and quite often is, because the auxiliaries are usually not controlled with variable speed drives, and all of them, and with optimization algorithms. If that's done, then it is cheaper to run 2 chillers than 1, whether they're constant or variable speed. Again, the same rules apply, that you need to be at lower head when you do that. So that myth was busted last time. The most efficient place to run chillers today is at part load. Myth number 2 was that chillers cannot run on cold tower water. That one was busted because if your chiller is designed to be able to handle oil eduction to get oil back to the sump, if your chiller is designed to be able to handle heavy loads or full load with minimum condenser water, then you can definitely, that's usually done with a variable orifice, then you can definitely handle low tower water and not only save energy but operate consistently and stably. Myth number 3, do not use VSDs on fully loaded chillers in a central plant. That one was busted because there's a misnomer, a misunderstanding of what is controlling speed. It is more often head that's controlling speed than load. Where we typically might save 30%, if you can vary both load and head, you can see here at the bottom that I'm saving 17% just on changing head alone, because last time we were strictly looking at 100% loaded chillers all the time. So you can still save because head is a major factor in saving with variable speed drives on chillers. Myth number 4, variable speed drive only saves energy on a single chiller. Well, if you remember from the myth a couple of times ago, a couple of bullets back, having heavy loads on chillers does not preclude saving money. So, but running all your chillers at part load is better when you have variable speed and you have low head. Myth number 5, a 0.5 kW per ton average best-in-class chiller plant. Is this a best-in-class chiller energy plant? No, that was busted because a variable speed drive average can be at 0.35 to 0.4. Points as low as 0.2 kW per ton can be hit, so that one is busted. So that was the 5 myths. We quickly reviewed those, and up next we're going to talk more about how we can look at the whole central plant instead of just the chillers. So we're going to start off by looking at kind of a base case where we present the basics of a primary secondary, and then we'll look at VPF. Primary secondary plant works like this. I have a primary loop over here that is constant flow. I have a secondary loop over here that is variable flow. One formula that you really need to take away from this presentation is that load is equal to flow times delta T. Load is always equal to flow times delta T. It doesn't matter if it's in a coil, it's in the evaporator of the chiller, it's in the cooling tower, it's in the condenser of the chiller. Every place in the system, load is equal to flow times delta T. In particular, in the primary loop, the load varies with delta T because it's constant flow. In the secondary loop, it's flow that varies and delta T remains constant. If we look at a design of a system and we attach some numbers to it, we're going to look at 3 2,000-ton chillers doing 56 to 40 degrees for 9,000 GPM in the primary, and we also have 3 secondary pumps for which we're looking at 9,000 GPM in the secondary. In the secondary, we know that our delta T is going to be from 40 to 56. It's going to remain constant. And over in the primary, the flow is going to remain constant, and delta T is going to vary. So at 100% load, this is what I look like. When I go to 75% load, flow is going to vary. In an ideal system, flow is going to vary with load. So my 75% load is going to reduce my flow of water from 9,000 to 6,750 here. And over in my primary loop where I have constant flow, then I'm going to still be at 9,000 GPM because I have to run all 3 chillers, because if I shut one off, I'd have 67% capacity and 75% load. So I got to run all 3 chillers. So 9,000 GPM flows over here, 6,750 flows in the secondary. So the extra or excess flow goes through the common pipe. When I go to the next at 50% load, now I can shut a chiller and a pump off, and I'm down to 6,000 GPM in my primary. I'm at 4,500 in my secondary, because 4,500 is 50% of 9,000. And the excess flow being 1,500 is pumped through the common. When I go to 25% load, I now can shut off 2 chillers and 2 pumps. I'm at 2,250, or 25% of 9,000. And in my primary, I've got 3,000 GPM, so I'm going to bypass 750. That's how a primary-secondary is supposed to at least work when it's under a load-based sequencing arrangement, which is the most common way in which it's done out there. So that presents the basics of primary-secondary, but now we need to look at myth number 6, which is going to be centered around primary-secondary to start with. Myth number 6 is that the water flow tracks the load. Chill water flow tracks load. That's the myth. Let's take a look at why it does not do that. A concept called low delta T syndrome is in almost every single plant in existence. It's just not a question of if, but a question of how much, to what degree it exists, because it usually always exists to some degree. Our design delta T here is 16 degrees. Low delta T means that when I go through my coils, I don't come out at 56, I come out at some lower value, perhaps 54 or 52, some lower value. That's low delta T. Now let's see what causes that to happen. First, we could have dirty coils, and I'll go in a little more detail on that particular one. We could have our controls out of calibration. We could have leaky two-way valves. Coils could be piped up backwards. We could have mixing of 2- and 3-way valves in the same system. There's probably 10 different causes of low delta T, but these 5 are the most prevalent and usually the largest, of which the 5, dirty coils, is probably the worst offender. When you're in a coil, the airflow goes through the coil. This is the entering air side over here, and I come through the coil to the leaving air side. I want my coldest water, which is here, going in where my coldest air is. So you can see that this pipe is located near the leaving air side of the coil. And this pipe is located near the entering, or the return air of the coil. The return water of the coil, and the entering air. So that, and my valve is usually located on the return side. How it works is there's, on the other side, in the leaving air side of this coil, in the back where you can't see, I have a temperature sensor that might be set for 55 degrees Fahrenheit. I'll talk all in Fahrenheit, in IP units. 55 degree Fahrenheit. The air enters the coil at roughly 80-67 and leaves about 55, 54.9, using the 40 degrees that comes out as 56. That's how it works. These very corners of the coil that you see here are the places where the coil starts to get dirty. And as it gets dirtier and dirtier, it'll form sort of a donut shaped, where the very center of the coil is clean and the very edges of the coil are dirty. So if you had a light on the other side of the coil and you shone it through and you look through it, you'd see very light in the middle and kind of a donut getting darker and darker. The ramification of a dirty coil is that the heat transfer characteristic gets worse. And that means that my leaving air sensor that's set for 55, that controls the valve that's on this return, to let water in and out of the coil is going to open up. The valve opens because it's supposed to maintain 55 degrees. Well, when I'm at design, then I'm going to be at design GPM. But when I'm at dirty coil, then I have to pump more water through it to get the same work out of the coil. Even though the load hasn't changed, the work through the coil has. It just can't do as much without more water, so we increase the flow. And if you recall from my formula earlier on, load is equal to flow times delta T everywhere. So if my load hasn't changed on the coil, then my flow has gone up. My delta T has to come down. So I can't pull out the delta T, the 16 degrees on this coil, and deliver 56 back to the system. It's going to deliver something less. And the same thing happens with all the other different things that were wrong with low delta T back here. All these things cause some sort of increased flow. So flow is out of proportion. You have more flow than a load needs. Okay? So now let's take a look at what that means. Under ideal operation, as you saw before, 100% load is equal to 100% flow. And I delta T is 16 degrees. Okay? Now, when I'm at 75% under ideal operation, 75% load means 75% flow. But what happens when I have low delta T? Meaning I don't have 16 anymore, I got 14. Now 75% load is equal to 86% secondary flow. So I'm now over pumping. Instead of having a need for 6,000 GPM, I'm pumping, 75%, which is 6750 GPM. Then I've actually got 7714. So I'm over pumping 964. Okay? If I'm over pumping the 964, now I've got 1286 here and 9,000 here. Once I add the 1286 that's coming through this common. These warm up, cool down the water so that when it enters the chiller, it's at a lower yet delta T. So the chiller's just not asked to do as much. But the point that I'm trying to make here is that this doesn't match. Percent load no longer equals percent flow. Let's take another look. Let's go to 67% load and see what happens. Because there's two things that happens here. One is that I have to overflow again, 76, which means I'm over pumping to 857. My 6,000 GPM that's over in my primary, because this one is off, I'm going to turn it off. I'm going to just shut it off because 2/3 capacity is what I have. So 2/3 capacity is what I need in terms of load. But I need more flow. I need 857 more flow. So what happens is when I shut this pump off here and this chiller off and isolate it, I've got 6,000 GPM in my primary. I've got 6857 in my secondary. So the last this 857 has to go backwards through the common. That 857 now mixes 54 degrees into the 40 degrees that's up here, delivering a mixed temperature of 41.7. The 41.7 goes out to all the coils. The coils see 41.7 instead of 40. They've got to open the valve more, so then it comes back warmer, and it keeps doing this until it cycles completely out of control. Right? So it's very important to keep enough flow so that you don't have this backflow happening. The second thing that's happening here is the only way in which I can keep that backflow happening is to turn on this pump. This pump that was off. Well, I can't turn it off. I got to leave it on. And if I leave it on, I got to turn on this chiller. I pump a dead chiller and just pump 54 degrees directly over into 40, which we don't want either. So you are forced, you are forced because of low delta T to run 3 chillers to do a 2-chiller job. Now that in itself is not a bad thing because you remember myth number 1 from last time. But what is bad is if you don't have optimal control and variable speed drives on your condenser water pumps and everything else, and you have all the optimal control going on, then it will cost you more energy. So that's another problem. There's more energy in the plant. Secondarily, I can't load up any of my chillers above, in this case, 87.5%, because the load up capability of the chillers is 14 divided by 16. That ratio of actual delta T to to design delta T comes into play, and I can't load up these chillers greater than 87.5 because my formula is load is equal to flow times delta T. My flow can't change because it's a design flow, a constant flow. My delta T is low, so you're just telling the chiller I don't need more than 87.5. The system isn't asking for it, so you can't load the chillers up. So there's a couple of problems that happen there. But this is rule number one about primary-secondary. You must keep the primary flow equal or greater than the secondary. Must always be that way or the system won't work. And that forces us to run more chillers than we need. It forces that we can't load up chillers. That's the negative impact of low delta T. All right. Now, here's another, So what we've done is we've busted that myth that flow tracks load. In real-world operating conditions, you'll always develop some sort of low delta T, so flow does not track load. Okay? The impact, we started to discuss that for a given flow, for a given load, pumps have to run faster and use more energy. So our secondary pumps are literally using more energy, so that draws more energy. I can't load up my chillers, and I have increased plant energy because of having to run more chillers than I need. The only way to solve low delta T is to mitigate it, is at the load. You have to clean the coils, you have to recalibrate controls, replace leaky valves, etc. You cannot solve low delta T at the plant, but you can mitigate it. It's just very difficult to do so with primary-secondary. Okay? Remember, load is equal to flow times delta T. The only way to do any mitigation with any pumping system is either to increase the flow above design or increase the delta T back to design or above design. You've got to do something with one of those two in order to mitigate the negative impact of low delta T. Okay? I can increase the delta T across the chillers. Well, I can't really change the return. I can change the supply. I can lower the supply down 3 degrees when I have a 2-degree delta T problem and pick that 2 degrees back up. I won't pick up 3, but I will pick up 2 because the water at going down 3 degrees here would be 37 degrees going to the coils. The coils would respond with a much better heat transfer characteristic that's nonlinear and actually pick up and pull 2 degrees out, so I'd have 36 to 53. I'd get my 16 degrees back. The penalty to doing that is that the chiller's energy is going to go up roughly 1.5 to 2% per degree for 3 degrees. But it's still better than having to run more chillers than you need under conditions where you don't have optimal control on your auxiliaries. Right. Now, another way in which I can mitigate low delta T is that maybe I can find a way to do something about flow, because doing something about delta T has a negative impact from more energy on the chillers. But a VPF system is another solution because it provides me with an ability to also go above design flow. So that's low delta T, and we busted myth number 6. Now let's look at variable primary flow. Here's our primary-secondary system up here, just for comparison. Here's our variable primary flow system down here. The difference is that I have down here bigger primary pumps because I'm combining primary and secondaries together into one pump. I have no secondary pumps. I have no secondary pumps to place. I don't have any space that I've got to use in the plant room. I don't have to wire them. I don't have to install them. I don't have to buy them. I don't have to rig them. I haven't got any of the costs associated with that. So typically, variable primary flow will cost less to install than primary-secondary. But I do have still some sort of bypass down here. With my primary-secondary, we have a larger bypass that's design criteria is typically the same size as the headers. It's usually 8 to 10 pipe diameters long in order to prevent transient temperature exchange, and it's usually designed to be as close to zero pressure drop as possible. This, however, is much, much smaller. It's designed to be the pipe is sized to be roughly the same as the minimum flow of the largest chiller you have, or operating chillers. So it's much smaller, and we do need a pressure drop, which we'll explain a little more about later. VPF also has the advantage that it improves the energy use over primary-secondary. The first reason is that we have better chill water pump energy consumption. One reason is because we have higher pump efficiency. This is because we're combining the primary and the secondary together and having a higher head with the pumps. Typically going to higher heads moves you into a more efficient region of most pump curves. And usually the pump curves for a primary circuit being somewhere around 40 feet will put you in 1100 RPM motors if, again, you're on 60 hertz. It'd be around 1150 RPM, and that usually is less than 80% efficient. When we go to one pump up at 140 feet, then we'll be up there in the 85% efficient range. We also have better energy from it because we have lower pump design head. When we were looking at primary secondary, the system we looked at, we had 40 feet ahead in the primary, and we had 115 feet in the secondary, 15 of which was because of the secondary pumps being there. They have headers, they have valves, they have pumps. There is also head loss there that no longer exists when we're in a VPF system. So a similarly designed VPF system will have 140 feet versus the 155 in a primary secondary. And as we lower the head, as you can see in this equation, and we improve the efficiency, the brake horsepower goes down. So between those two items, higher pump efficiency and lower head, I have improved the energy of the pumping system all throughout the year. It's always got something better. There's a third reason for energy savings that most people do recognize, and that is that if I have a third of my head in the primary that is all constant flow, constant speed, there's not much savings there, as opposed to the secondary where 2/3 of it's variable headed, and I get a lot of VSD savings. Now I've got the entire plant that's VSD, and all of the head is variable, so I've got that savings too. So there's three reasons why we have an energy use advantage over primary secondary. Now we have an additional one. We have less impact from low delta T because we can, with headered pumping, mitigate low delta T. We can't solve it. You got to do that at the loads, but we can mitigate it. Let's look at the same view we had of the primary secondary, but now VPF. Now we have our headered pumps over here. We have 9,000 GPM going in our total one circuit, 6,000 tons, design 9,056 to 40. When I go to 75% load, I still have a 16-degree delta T, and if I'm ideal, I have my 6750 GPM, 75% of 9,000, and everything's fine. When I go to 67% load, when I'm under ideal conditions, I can now, at 67%, shut a chiller off because my capacity with two chillers is 67% for the system. So I can turn off a chiller. I can choose to turn a pump off or not. Depends upon whether it's more efficient to run 3 versus 2. Those are algorithms that something like a CPO would do. I've used the term CPO several times. That's chiller plant optimization for those who may not know. And that's what the third webinar will be all about. Anyway, I can choose here, but the point is that I can now turn this chiller off. So if I have 3 constant speed chillers that don't have CPO on all the auxiliaries and so on, now I don't have to run more chillers than I need. I can just overpump these 2 chillers when I have low delta T, which is now. It didn't click. Oh, sorry. Yes, it did. Okay, now I've got low delta T, 67% load, but now instead of 6,000 GPM here, I have 6857, just like I did before with the primary secondary. So 6857 travels through the whole system, everywhere, and it reduces my delta T. I have 54, not 56 entering now. But I can shut this chiller off, and I can isolate it. And I can overpump these 2 chillers that are designed at 3,000 to 3429 and take care of having to run more chillers than I need. Just overpump these. And can I overpump them? Of course I can. Chillers can handle up to 11 or 12 feet per second. Typically designs are around about 5 or 6 feet per second. The design for the chillers that we pick for this example that we run calculations on later is at 5.8 feet per second, and you can turn it down to 1.5. Okay, and you can go up to 12. As long as you don't exceed the max pressure drop through the water boxes, which for these chillers, that are 2-pass is 45 feet. Right now I'm at 20 feet at design, so to go to 3429 is a 15% increase in flow, and therefore I'm going to go up to 26 feet instead of 20, which is below the 45. So I can definitely push a lot more flow than what I'm showing here, but it shows you how low delta T can be mitigated in the plant because I can overpump chillers. Going back to our equation, load is equal to flow times delta T. The delta T is down, so I move the flow up. Problem solved at the plant. Now I still have to overpump, so I'm still running these pumps too fast, but I have no choice to do that until I decide to go out and clean my coils, calibrate my controls, fix leaky valves, etc. Okay, so myth number 6, once again, is busted. Even with VPF systems, flow does not track load, but the impact, the negative impact of it can be reduced in the plant. Okay, myth number 7. Chilled water pump speed tracks flow. A moment ago we said flow doesn't track load. Now we have a new myth that speed tracks flow. Okay, let's take a look at this is a head capacity curve up here, and this is our ideal system curve to 0. And you'll see that as I reduce speed down to 50% right here, my speed, as I reduce flow, I'm at 50%, my speed is at 50%. So when you have an ideal system curve going to 0, the affinity laws apply, and speed tracks flow. But that's not what happens in chill water systems. I have a set point, some pressure sensor out near the end of the system that's got to be higher than whatever the last coil and the last valve is. So I've got to set it up to some number. I've picked 30 feet here. Now you'll notice that I'm not operating here anymore. I've had to increase speed to be up here to cross that curve. Now I'm at 62% speed to do 50% flow. It even gets more interesting because it's not really a curve it follows, it's an area. And what happens with chill water pumping is that I could be operating down here or anywhere in between. If I'm up here, it means that, when I'm in the perfect condition, I'm following as ideally as I can. All the loads in the building are exactly the same percent load. So if I'm at 70% load on one coil, I'm 70% load on all coils. But that's not real. If I have the coils that are far away from the plant, the most active, the highest loaded, and the ones closer not, I'm going to be operating up here in the head area. If I have the coils that are close to the plant that are more active, then I'm going to be in the lower part of the area. So you're actually operating all in this head area all the time. And what you notice is that I could be at this head, I could be at this head. And if I'm at this head, my speed here will move down to here. If I'm at this head, my speed will move up to here. So speed for the same exact flow can be infinite. You got an infinite number of heads, you got an infinite number of potential speeds you could be at, all for exactly the same 50% flow. So speed does not track flow in a chill water system. Okay? So that myth is busted. And there's a derivative to that myth, and that is that if speed doesn't track flow and flow doesn't track load, then speed doesn't track load. And you really need to use flow times delta T to calculate load. That means you really can't avoid flow meters if you want to optimize your plant. And remember, the whole seminar is about how to design the plant for the best efficiency. You need flow meters, and you need good flow meters that can measure well and stay in calibration. Okay. So we finished busting myth number 7 about 6 and 7 that were about flow and speed, and now we want to look at some design considerations for VPF. And we'll look at them for the chillers and the pumps and the towers, but starting with the chillers. First of all, equal-sized chillers are preferred but not required. There's a misnomer out there that you have to have equal-sized chillers. It's better if you do. It's easier if you do. What's more important than having equal-sized chillers is having equal pressure drop across each chiller. So they can be different sizes. It just makes the math a little more complicated when you're trying to do calculations in balance. And it's also more difficult to keep them in balance when you got folks going around cranking balancing valves and not putting them back in the right place. So it's better, but you don't have to. you have to keep operating to stay within minimum flow. So you can't go below 1.5 feet per second. Every chiller manufacturer has got GPMs they can give you for that. So you got to maintain flow above that, which is why we use the bypass valve. And you can't go above max flow rate or you'll destroy the tubes. You'll wear them right out. And that's usually 11 to 12 feet per second, as I said earlier. And it's 45 or 67 pressure drop, depending upon whether it's a 2 or 3 pass shell. Modulating isolation valves are going to be necessary. You'll see why in a few minutes, as opposed to a two-position valve. Two-position strokeable can work if it's linear. Valve position the flow. Set them to open to 1.5 to 2 minutes, linear proportion, and I'll show you an example of why that's important with a VPF system in a few minutes. Chillers also, a major consideration is not to vary flow too quickly. This is the major thing about variable flow through chillers that 50 years ago, 20 years ago, 10 years ago, people were saying you can't use variable flow. It's all has to do with chillers. But you can use variable flow with chillers nowadays, at least probably over the last 10 years. Most chillers can handle variable flow, with the exception of maybe absorbers. Okay? The typical setting for variable flow rate is about 10% per minute. Most HVAC systems don't need more than 5. Most of the buildings that have been done by the folks that are going to give you the next webinar usually set them around 5 because they just don't need faster than 5. The building doesn't call for it. Only in special circumstances where you got some big load that drops off, like a process load or something rather. But with normal HVAC, 5's plenty, so we usually set them to 10. That doesn't mean they can't go faster. You can set these maybe up to 30. Some systems are 5, some are 10, all the way up to 30. It's not the chiller determining exactly how fast you can go. It's the system determining it for the chiller. Okay? The way you set this is typically in the variable speed pump drive controller. Go to the panel on the pump and go to look for the ramp function on the variable speed drive. It's usually in seconds to go from 0 to max speed or max speed to 0. It'll be an accel rate and a decel rate. Acceleration rate, deceleration rate. It'll usually default to about 60 seconds, which is 100% per minute, far too fast for any chiller. So you just change that to 600 seconds, there's your 10% per minute. If that's not fast enough, then you'll see your chill water fluctuate. This can all be done during commissioning. Your chill water will constantly fluctuate temperature. It can't seem to settle down. Then you need to increase that speed. So change 600 seconds to 450. That's 15% per minute. On the other hand, if it's too fast, then you got to slow it down. Too fast is because you'll be going off on nuisance trips under low water temperature cutout. Okay? Now, the type of chiller can change how much and how fast you can vary flow. Flooded evap, DX, centrifugal absorption. Absorption maybe 3% per minute if you're lucky. But centrifugals with flooded evaporators can handle the most. VPF, in case, I should mention that variable primary flow, if anyone doesn't know what I mean when I say VPF. The next thing that affects how fast you can change is the system water volume, the capacitance, the thermal capacitance of the system. The bigger the system is, the more gallons of water in the system per ton that you have, allows you to vary flow faster and faster and faster in the same chiller. What I'm saying is a chiller can be put in one system in one building, and 5% per minute might be as fast as you can go, because it's a small system. On the other hand, you can take that exact same chiller, change nothing about it, and put it in another system, and it's 30% per minute. So it's not the chiller determining this, it's the system you connect it to. So the bigger it is. Another way that I like to explain this particular phenomenon is when a gallon of water leaves the chiller and goes out to the system, breaks up and goes around to everything, and then reassembles in the return and returns back to the chiller, the amount of time that takes to leave the chiller and return, the longer it is, the faster the chiller can handle the rate of change. Okay? chiller's load changes what the rate of change is. If the chiller is fully loaded, it can handle its maximum change, whatever that might be. If in a given system 20% happens to be maximum, then it could handle 20% at 100% load, but when you're down at 10% load or min load, it'll literally shut off if you lower flow. There's no place for the vanes to go. They're fully closed. They can't close anymore. Right? Active loads, where the loads are active in the system. If you remember that from the speed chart we were looking at in the head, where you got the head area, when the loads are active far away from the pumps, then you're going to higher heads and higher speeds. Well, and same thing kind of happens here. The loads that are active far away from the plant means that gallon of water leaving takes longer to return. So even though on average it might be 20%, when all the loads are active far away, you can actually go to 30. On the other hand, if the loads were active close to the plant, then it might drop to 10. So you see, the important thing to gather from this is that there is no one number for all conditions, and it varies all the way from 5 to 30%. Right? There's another thing that has nothing directly to do with the chiller, but remember, with a VPF system, I'm no longer isolated from what happens at the air handling units. When I'm in primary secondary, I'm hydraulically decoupled from what's going out there, out in the secondary, from flow and head changes as I change valves and so on. But no longer am I. And that means that you don't want to shut a bunch of air units off at once and close their valves, because you'll get a sudden change in flow, and that will trip the chillers off. So sequence the air handlers on and off, in 15-minute intervals, 10 to 15-minute intervals, so you don't have that problem. All of the ones we just discussed are during normal operation. You could have a nuisance trip if flow varies too fast through chillers, and how to deal with that. But there is another case where you can go too fast, and that's when you're staging chillers on. Here's an example where I have this chiller at the bottom running. It doesn't matter how many pumps I've got running. You can run two, I could run one. It's up to my algorithm, however I want to do that, because they're headered, and they're variable speed, so I can do it any way I like. But over here, this chiller is the only one running, the one I'm pointing to. I want to add this chiller. Okay? Whatever the conditions are, in this case, my flow has started to increase, and I'm going above, so my chill water is starting to rise. Whatever the reason is that you now need to add another chiller, then the very first thing that I have to do is open its isolation valve of the chiller I want to add. Now, a moment ago, down here with this chiller, I had 3,300 GPM. I open a two-position valve that might take 10 seconds to open, maybe 15, and all of a sudden, I've halved the flow in this chiller down here. This chiller is got inlet vanes inside of it that take 2 minutes to close, to go from 100% open that it was a moment ago, full load. It wants to go to 50% load because it's sharing the load with the other chiller. It wants to get to 50, so it starts closing the vanes, but it takes a minute and a half for those vanes to get to the 50% load position, which is roughly 30% vane position. So it can't keep up with the 15 seconds that it took to close this. So this chiller that's almost fully loaded sees up here in our formula where load is equal to flow times delta T, it sees half the flow all of a sudden. So the only way it can do almost full load at that condition is to double the delta T. So my 57-degree return temperature is driven down to 25 degrees here. Okay? So 25 degrees, of course, is never going to reach because the low water temperature cutout is going to kick out 4 degrees below set point standard. So my 40 degrees, when it gets to 36, off she goes. And you can imagine what a nuisance that is when you have this chiller running. You just want to add the second one, and this one trips off on you. It all does it because this valve that's here is two-position, just opens in 10 or 15 seconds. This is why I said earlier we need modulating valves to open up over the course of 1.5 to 2 minutes. Okay? That way it solves that problem. This opens as fast as the vanes close and the problem goes away. Okay? Another consideration with VPF systems and design and control is energy-based sequencing. Energy-based sequencing is when you look at what we have typically always used, load-based, and you mix it with energy-based depending upon conditions that are going on with the weather. When you're at high head, remember to run your chillers at high load, which is load-based type sequencing. When you're at low head, you want to run at low load, which means you want to run 2 chillers to do a 1 chiller job. You want to run 2 pumps to do a 1 pump job, etc. Typically, not always. It depends upon where you are in the pump curve and where the efficiencies lie, but typically you want to run multiple units here and you want to run single units here. Okay? Now, design considerations about pumps. One, of course, we want a header arrangement because, as you recall from VPF, how we mitigate low delta T is to overpump chillers. Well, how do I overpump them if I dedicate pumps? Well, that's not so easy to do. There are ways to do it, but headering's the best way, and it's not going to cost you any more to do it that way than any other way you can think of. You've got to be able to overpump chillers, and headered will do that. Plus, it gives you the reliability of being able to run any pump with any chiller. Okay. Sequence these pumps using energy-based type sequencing because we are talking about doing high-efficiency plants. So you want energy-based sequencing that you'll learn in the next webinar. But we must stay within the pump and the motor limits. Don't go too slow with pumps because you may not be able to lubricate the bearings when you go below 25%. And when you go below 15 hertz, which is 25% of 60 if you're on 60 hertz, and of course it's a little higher with percentage-wise, it's 50 hertz, but going below 15 hertz on motors can quite often have the problem of eddy currents and overheating and so on. So we want to make sure that we stay within the pump's limits. Speed should be controlled by 2 possible methods. One was pressure and the other is valve position. With pressure, we want to make sure we do not locate the pressure sensor in the plant ever, not to control ultimately the speed forever. There's a way in which you can do it from the plant, but I'll explain that in a minute. We want to have it not 2/3 of the way down the system. We want it all the way to the end of the system. So you want to be on the index circuit as far as you can possibly be near the longest run or the most resistive run all the way out to through the index circuit. If you have wandering index circuit, then put in more than 1 pressure sensor and choose the highest. Okay? Now, these pressure sensors that control variable speed drive need to be direct wired. Other variable speed drives can hunt. Don't connect a pressure sensor through the network and have it fight network traffic to control variable speed drives in the plant. They need to be direct wired. Now that can be a problem locating at the end of the circuit when you're clear across a parking lot to another building. So there are ways in which you can locate a pressure sensor in the plant that gets reset. That one in the plant is actually controlling the variable speed drive. So you get that direct control, the fast-acting control, so you don't hunt, but it is controlled through the network by the pressure sensors at the end. Now it'll work. It's called piggybacking. So the pressure sensors at the end are constantly resetting the pressure in the plant that controls the variable speed drives. The more optimal way to do it is to vary speed by valve position. You find the worst valve in the system because if you're monitoring all of them, you can find the worst one. And you want only one valve to be near 100% open, and so you control the speed that way. That way you can slow down even farther at every load, just about every point, just a little bit, but it squeezes some more energy. Okay? The bypass piping that we're looking at that maintains minimum flow through the chillers. You size that pipe and valve for the minimum flow of the largest chiller, or of the operating chillers if you happen to have more than one that are operating at a condition where you're actually at minimum flow. It can happen, but usually it's just one chiller. Whatever the largest chiller is what you size it for. And it needs a pressure drop. We usually recommend that when you're down to a minimum flow condition, there's hardly any resistance head left in the whole system. The only thing that's left is practically the set point at the end of the circuit. So if you size the pressure drop with the bypass valve fully open to be the same as the set point, you'll be able to get good controllability. You can move water through the bypass or out to the system very easily. But the point is unlike primary, secondary, where I want zero pressure drop, I do want pressure drop here so that I can move water in either direction easily. Okay. Again, with primary, secondary, we do 8 to 10 pipe diameters with zero pressure drop, but here I'm trying to get the pressure drop in this. So it's much smaller. In fact, quite often, the bypass valve is sized one size smaller than even the pipe to increase the pressure because it's not easy. So this is a small pipe versus primary, secondary. Primary, secondary is a large pipe. What it does is, as we said, maintain minimum chill water flow through operating chillers. It can be done one of two possible ways. Flow meter is preferred. I'm going to mention it first because it's much more accurate, and I can get closer to the minimum flow of the chiller than I can with a pressure sensor. The differential pressure sensor has the negative point. I have 20 feet of pressure drop at 3,000 GPM through these chillers. If I go down to minimum flow and these chillers of around 7, for these chillers is 776 or just about 25% flow, then it's like 0.25 squared. 0.25 squared is 0.0625 times my 20 feet, which means I'm at 1.2 feet. Let me rephrase that again. When I'm at 3,000 GPM, I'm at 20 foot of pressure drop. But when I drop all the way down to 776 GPM, the minimum for this chiller, I'll be at 1.2. Now try to find some pressure sensor that you can control from that can monitor and measure that level. So you end up having to set your minimum flow much, much higher so you don't drop below dead bands and so on. So it is a much more accurate system to use the flow meters. You can go to lower flows so that when you are in bypass, then you're not wasting as much energy. Here's a typical situation with the 776 I mentioned. I've got, in this case, I'm down at minimum flow. I've got just this one chiller running. I happen to be running one pump in this case. It's delivering 776 GPM. Because this flow meter down here is controlling this valve to maintain 326 because my system wants 450. I can't go to 450, so I've got to stop and open this valve so that I maintain 7076 here when I got 450 over here. This protects the chiller so it doesn't freeze. Okay? That's how minimum flow works. Bypass valve, we talked about these things up here. We also want to have a high rangeability for the valve, 100 to 1. Rangeability of a valve is the max flow that the valve can handle, ratioed against what's the minimum controllable flow that the valve can handle. We need to have PSID ratings for static, dynamic, and close-off equal to shut-off head of the pumps, technically, plus the fill pressure. What the static rating is the casing of the valve. If you don't have enough pressure differential rating on that valve, you could burst it. The dynamic rating is the ability for the seat to remain in place and not blow out because the pressure differential is too great. And the close-off rating is the torque of the motor, the actuator on the valve. Is it got enough torque to close down under the pressure differential you could see of shutoff head? It's possible to see it in the system. And if it can't close, it'll sit there and chatter. Okay? So PSID ratings need to be up near shutoff head of the pump for static, dynamic, and close-off. This bypass valve needs to also be linear proportion, just like those modulating valves, isolation valves for the chiller. I can't get good control if I use a butterfly valve that just opens 20 or 30% and you get 80% of the water. The real thing that's important is that it be linear with time. Linear proportion will usually give you that, but you could use a butterfly valve if you were controlling how fast the valve opens with automation software. Open it very, very slowly at first so you get kind of a linear proportion with time. And then the bypass valve will work just fine. It needs to be a fast-acting actuator. The fast action is needed for this to protect the chillers from freezing. Just like the control for the variable speed drives on the pumps, the control for this also needs to be fast-acting. And what that means is that you need to locate it so that you can direct wire it. It doesn't matter for the function of it to where it's located. It can be at the end of the system, it can be beginning right in the plant. And it'll function as long as you have it direct wired. We usually recommend that it's put in the plant, one, because direct wiring is easy, and two, I get the amount of the time that I need, and I save energy. Because if I put it all the way out the end of the system, the bypass flow in bypass mode has to travel through the entire system all the way to the end and come back. And that's just wasting pump energy during bypass operation. So locating in the plant saves energy, and it also makes it easy. So that's the design considerations for VPF on the chill water side. The next is myth number 8, and we're going to turn it over to Bill.
Okay, thank you, Roy, very much.
You're not.
No.
Okay, Bill's going to work from my computer. It's going to be him talking, but you're going to see my name in the every time he clicks on an arrow somewhere.
That's okay. Thank you, Roy, very much for getting that far. We've now gone through 2 more myths, and we've made the chiller plant, at least on the chill water side, what we want to call optimized ready. And now we're going to go into number 8. And myth number 8 is pumps and towers use more energy than chillers can save. First, we're going to look at a typical condenser water system, constant speed, dedicated pumps that you would normally see with not only with the primary, secondary plant, and we still have the same rules as we had before. Cooling tower load is flow times delta T. Here's a typical diagram. We have the condenser water pumps, dedicated per chiller. We have cooling towers. We have a typical 18,000 GPM total for 100% plant load. And so the real question is on total plant energy, when I slow down the condenser pump and the cooling tower fans, will my plant energy get higher or lower? And that's what we're going to talk about here. Some of the considerations that we are going to use in this analysis that we did our calculations, we use the same plant as was described in the first part of this presentation, 2,000-ton chillers and the flows that are associated with a standard plant. We assume 6,000 hours of annual operation, and we assume the load is load-based sequencing for a primary secondary plant. And when you do that, the average component load varies, of course, but it's going to be around 70%. In our case, it landed at 72%. For a VPF, we're going to assume energy-based sequencing, and when you use energy-based sequencing or a CPO type of control, the average component load drops. In this case, it ended at 58%. We reduced our condenser water flow, but we also know that when you reduce condenser water flow, you're going to get an increase in your fouling rate. We took that into account. Condenser water flow rate and cooling tower fan flow, we reduced it to 80%. Now, we looked at several different reductions. We looked at 90%. We looked at 80%. We took it down to around 70% where we saw a crossover. There are many considerations. We'll get into that later on. But we ended up at 80% reduction in condenser water and cooling tower airflow. As before, all the chillers have VSDs, variable speed drives. The primary secondary system had variable speed drives on the secondary chill water pumps and also on the cooling tower fans. The VPF plants were equipped with variable speed drives on the pumps and cooling tower fans. We did not include any impact of low delta T. That is going to be left for another analysis. So here are the results of this work. First, we analyzed a primary secondary plant that was described earlier, and on the assumptions just given, the chill water pumps use approximately 1.3 million kilowatt hours, a little bit more than that, 1.4. The condenser water pumps used 1.4 million kilowatt hours. The cooling tower fans, 1.1 million kilowatt hours. The chillers, even though they were VSDs, they used 12.9 million kilowatt hours. A total for that that year was 16 million, almost 16.8 million kilowatt hours. And again, that was based on the three 2,000-ton chillers. Next, we looked at the VPF plant, energy-based sequencing. You can see the immediate savings in the chill water pumps were now around 629,000 kilowatt hours annually versus the 1.4 from before. The condenser water pumps are roughly the same. The slight difference in loadings when we use energy-based sequencing. Cooling tower fans were approximately the same, but now you can see the effect of energy-based sequencing on the average chiller load. Instead of 12.9 million kilowatt hours per year with the variable speed drive chiller, we now can achieve 8.6 million kilowatt hours per year, and now the total energy for that plant is 11.8 million kilowatt hours. Last, we tried to answer this question for this myth. What happens when we reduce the condenser water pump flow or the cooling tower airflow with variable speed drives? As I said before, we ended up at 80% of design flow, and now you can see the savings. The chill water pump, of course, remained at the same savings as the previous column, but now the condenser water pump energy went from 1.5 million down to 843,000 kilowatt hours in 1 year. The cooling tower fans energy was reduced from 1.1 million to 569,000 kilowatt hours per year. As expected, the reduced condenser water flow and reduced cooling tower fan flow and the increased fouling of a reduced cooling tower water flow had an increase in chiller energy. We went from 8.6 million up to 9.3 million. However, as we were interested to find, the total net energy for that plant went from 11.8 million kilowatt hours down to 11,349,000 kilowatt hours in that year. And that means that myth number 8 is busted. Reducing condenser water flow and cooling tower airflow does save more energy than increase energy on the chiller down to about 80%. Now, if you go too far, then yes, it will increase. But we found that there is a optimum condition. To achieve this, of course, you have to look at some design considerations. One of the most important on the chillers, you need to make sure that the chillers can provide full or greater capacity at low entering condenser water temperatures, down to 50 to 55 degrees Fahrenheit. Also, at reduced entering condenser water temperatures, keep in mind that centrifugal chillers can often produce more than design load. And here is a graph of that. Over here on the right is percent of the original kilowatt per ton. And on the left is percent load. As you can see, at 85 degrees entering condenser water temperature, the chiller is at 100% load. As I reduce an entering condenser water temperature, you can see the kW per ton decreases. But as noted before, with all centrifugal chillers, and under those conditions, you can also achieve more capacity than design at reduced tower temperatures, and at the same time lower kW per ton. On the condenser water flow, we still recommend staying roughly 80%, go no lower than 80% of design flow minimum. And there's lots of reasons. We'll talk about that. It mainly affects the condenser. But also keep in mind, even though you're saving energy, you still are increasing your fouling along the way. So we must stay above 3.3 feet per second, or your tube fouling becomes asymptotic. And that means that at full flow, you have your standard fouling. The fouling will still increase as you reduce in flow. So you don't get everything for just reduced flow. Don't vary the flow too fast. Again, we recommend 10% per minute. There's no reason to, and going too fast can often give some instabilities. Don't exceed 12 feet per second or 45-foot pressure drop roughly for our 2-pass chiller. You can go a little bit higher, 67 feet for a 3-pass. Again, for the same considerations on chill water flow, you have the same limits on condenser water flow. The cooling tower. When you talk to your cooling tower manufacturers, you'll find out quickly, if you don't know already, that they do not like varying the flow more than plus or minus 15% from design. When you're varying the cooling tower water too low, it creates dry spots, and that increases the approach on the chiller, which increases the energy used by the chiller. When you get too low, that also increases the cooling tower maintenance. You have to clean it more often, and in the wintertime, for those in areas where you can freeze, you can have freezing on the peripherals, and you can get some damage from that as well. On your condenser water pumps, again, as on the chill water, a headed arrangement enables you to optimize their usage. And of course, more importantly than all these, is using an energy-based sequencing, or a CPO, to take advantage of the capabilities of the plant. You still need a balancing valve on your condenser water systems and chillers. You still want to minimize their use. One of them, when you balance everything, should be fully open. And now we're just going to summarize everything that we talked about today. We talked about 3 central plant myths. They are busted. They were, number 6, the chill water flow tracks campus cooling load. That's busted. With VPF systems, they mitigate the negative impact of low system delta T. Myth number 7, we talked about, said chill water pump speed tracks flow. That is busted. There is always some kind of control, static head, or other considerations in variable speed systems. You really need to use flow meters to track flow, but more importantly, to get the most efficient plant operation. Myth number 8, pump towers use more energy than chillers can save. And we busted that. We have proven that reducing condenser water flow and cooling tower airflow can save more energy than the increase in energy on chillers, down to around, at least for the case that we chose, 80% of full design flow. In summary, speed does not track flow, and flow does not track load. When you reduce condenser flow and cooling tower airflow, saves net plant energy, even though chiller energy increases as long as those reductions aren't too low. A header VPF plant also can be used to mitigate at the plant the negative impact of low delta T. The next myth, which we'll save for the next session, is that CPO is an off-the-shelf control system. And you'll have to come back for the next session to find out if that myth is or is not busted. And with that, I'll turn it back over to Laxmi.
Thank you, Roy and Bill, and thank you to all the attendees who have sent in questions. We hope you have learned something about the topic that was presented today. We did focus on the chiller plants today. On the plant design, we looked at the chillers and variable speed drives last time, and the last session, which will be December 6th, we'll look at CPO, or chiller plant optimization. So we have a few questions, and I'm just passing them on to Bill and Roy so they can take a look and prepare to answer the questions. We still have a few minutes, so if you want to put in some additional questions, we'll be happy to take care of them now as time permits or after the webinar. We started about 15 minutes late, so we'll go to about 4:15. And so Bill and Roy, I hope you can see the questions.
Yes, we can.
All right. So Cheryl, if you could pass control over to Roy, they can begin to answer the questions.
Okay. Okay, first question was proper design and maintenance for coils will avoid all these problems. I assume the questioner was asking about low delta T. Of course, if you keep your controls calibrated, if you ensure that you don't have leaky valves, if you clean your coils, if you're a consulting engineer out there and you want to help the owners clean coils, then give them access on both sides. Because a cooling coil, typically a spray cleaning method is used, and you can only spray in about 4 rows deep, and most engineers have at least 6 rows for cooling coils, so you got to be able to get to both sides. The typical answer to that, of course, is you got coil pull, and that's always provided to get the coil out, and then you could clean it. But now you got to disconnect all the piping and everything else. So if there is not an issue of budget and there's not an issue of space, then put an access section on both sides and make it easier to clean the coil. So yes, you are quite correct that it's not just design, but it's also, in fact, there's a little bit of design there. If there's a way to give more space, that's a design issue. If there's a way to provide access both sides, that's a design issue. But that's not always the case because we're usually over budget on a lot of projects. In any case, yes. So the second question is differential pressure sensor on the index circuit or on each chiller. Well, if I were using differential pressure, you could use it on the circuit. But typically it's put on each chiller if you're going to use differential pressure instead of flow. If you use flow meter, the best way is to put flow meter in each chiller. But that's not always possible, not because of expense, although that's also a consideration. It's just that you may not have enough pipe diameters on either side of the inlet or outlet of the chiller to do it. So you can put it oftentimes in a common place on a return and use math to come up with hitting minimum flow. Is it perfect? No. What's more perfect is each chiller, but you can't always do it. But the pressure differential one, I would probably recommend if you're going to use that technique, put it on each chiller. Next question, VPF makes sense for only 2-way valve loads. Correct. That's correct. You don't want to use any mixing of 2- and 3-way valves because you're guaranteeing yourself low delta T, which includes not putting 3-way valves at the end for overpressurization. Add a 2-way valve for that. Let me see what else we have here. Could you quickly explain the advantage, disadvantage of 2- and 3-way valve? Well, 2-way valve systems and 3-way valve systems. Well, 2-way saves energy because you're not pumping water that you're not using. 3-way valve systems probably use, I'd say 40% more energy, 40 to 50% more energy than that primary-secondary system you saw. 40 to 50% more energy on chill water pumping, just that portion, chill water pumping. So it's a big difference in energy to go 2-way valves and variable speed than it is to stay with 3-ways. Next question, should chillers have spare capacity? Chillers typically already have spare capacity. That's because generally when engineers design buildings, they'll come up with a tonnage and put in some extra because they really don't want to be wrong. Okay? So there's usually spare capacity there already, and as time goes by, you usually develop it. If you're not increasing the building or doing something to change it or adding things, adding space, etc., then usually you're doing things like better insulation, more window films, etc., and you're reducing load. So you kind of end up with spare capacity. But again, if you are expanding, then you're running. The spare capacity can be handy to, for expansion, for future. Question is, what is PSID? That's pounds per square inch differential. It's pounds per square inch is nothing more than like KPA or bar differential. So it could be KPAD, it could be bar D, or PSID. It's just the units in IP. But it's a rating for static, dynamic, and close-off pressure differential you can put across the valve and still have it work properly. Question, what was the pump program you was using to show changes of flows on the system curve? That is a pump program that we're developing. It's going to be built into our YorkCalc software for those of you who have YorkWorks. And that would be for single and multiple pumps here next year. So it's kind of a beta version of the single pump engine. Next question. Okay, what about using load limiting on running chiller when enabling a second machine? This is regarding going back to adding an additional chiller. What he's suggesting is that we could load limit or demand limit the machine and accomplish essentially the same thing. Force it down to 50%. He's absolutely correct. But that's not always adequate. That's the only reason we recommend the modulating valves, is that they always work, and load limiting may not work. I mean, it usually will, but it may not work well enough. You still may have the nuisance trips, but most of the time it will. You can also reset the chill water temperature up 4 degrees and unload the chiller that way. You can also, if you're concerned about getting temperature, keeping your chill water from rising too much, like data centers, you can utilize that bypass valve for a secondary function. Whenever you're adding a chiller, open it. And what you effectively do is starve water out at the end of the system, so the pressure sensor drops. The reading there drops, so the pressure sensor says, hey, I need more water. So it'll tell the variable speeds to drive up, to speed up. And that's what we want, is more flow going through the chiller that is about to kick off on you. So that'll help work. Plus, we'll be bypassing some cold water. The 40-degree water will be, more of it will be mixing, maintaining your temperature better, so that you don't lose control of the chill water for the 5 minutes doing the changeover. Next question, why is the focus on designing plants to compensate for low delta T? You're absolutely right. We should always design everything and be able to operate it, but it's not the same people doing it. The engineers are usually designing it so they can put in things to make things better. They actually do by forcing, many engineers will say, I want 6 rows on the coil minimum. Even if a 4-row coil will do the job of 80, 67, cool down to 55, 54, they'll still say, I want 6 rows minimum. What they're doing is mitigating the delta T problem. They're prolonging it before it can happen. Again, putting the access on both sides, so there can be some things that do that. But the main reason we're focusing on it is that it's real. Low delta T is real. It's in all plants. The question of to what degree it's there, and that has a lot to do with the training programs and the maintenance and the operation. So if those things are all done and you clean the coils every year and you do all those kinds of things, then low delta T is going to have a very minimal impact. So you don't have to concern yourself with it. But that just doesn't happen to be the case with most plants. Okay. Let's see if we got some more. It looks like there's some more down here.
No, that's it.
What? Hold one. Okay, that looks, maybe there's some more down here. I'm trying to scroll down. Here's one. Yes?
Laxmi just sent you some more of the questions in the chat box.
Yeah, I see them now. I'm scrolling down. Can we run the chiller at full load for a long period of time when we have another standby chiller available? Some people say it's not good to run at full load for a long period of time. I don't know of any reason why you can't run at full load or even above that for a long period of time. The main thing to be concerned about is not so much whether you're at full load, but are you at your high head. If your head gets too high and you start doing CPO algorithms that lower flow in the condenser, then you could literally put your chiller in surge. There's a more consideration for that, but running at full load, it really shouldn't hurt your chiller if you ran that way forever. Let me see what else. Can you use a Belimo PICCV pressure-independent automatic control valve? You can use pressure-independent valves, sure. The pressure-independent valves have value. The bigger question isn't so much, do they work, but whether they provide enough savings to justify the additional cost. because you do have, you usually have to have at least about 5 psi at the valve to make it work. So there's issues with it being a little higher in that respect, and then it saves in another respect. So it does save net overall, but does it save enough to justify the higher cost of today's valve? I'm not sure about that one. The jury's out. Okay. Condenser pumps are variable or constant flow. In the primary-secondary system, the condenser pumps were run as constant flow, but we actually were putting VSDs on those pumps to eliminate balancing valves, but they were really running as constant flow. Over in the VPF system, the first VPF in the middle column there, we were running energy-based sequencing without doing anything to lower flow. We were keeping it constant. And the third column was when we lowered the flow down to the 80%. So all of the equipment in there had variable speed drives on it. It was really just a question of whether you ran them as variable speed drives. Variable speed drives can replace the functionality of a balancing valve and at least keep one of them open so that you don't waste head in the entire system forever through a balancing valve. And they're cheap enough now that it's worth it. Let's see what else. How would you optimize control VFD condenser water pump and VPF systems? How to balance flow over chillers if they have a different rated capacity? Well, you could put a pressure sensor and vary the speed depending upon what chillers are running. You could have an algorithm to vary the speed with load, meaning to maintain delta T across the condensers. Whatever condensers you got, maintain the delta T. As long as they're balanced to start with, then they ought to ramp down at the same basic proportion. So maintain delta T is a good way to do it too. That's the same thing as saying I want to reduce with load. So in our case, we would be reducing to our 80% utilizing the maintain delta T. They'll use a little different algorithm over at CPO30. You'll have to ask them because they keep that pretty well under wraps because they're all proprietary. But that's how I would do it, vary with load. So when your whole building is down to 80% load, I'd be at 80% flow on the condenser water pumps and 80% speed on my tower fan. The tower fan would remain there until I got to minimum condenser water rating. I can't go below on the chiller, be that 50 or 55, and then it would start slowing down again. So it has a slow down with load down to 80, and then once you hit 55, it slows down to whatever speed it's got to maintain that 55. Okay, what is the best hold on one second. I sort of lost my place, so bear with me. What is the cutoff temp for cooling tower? I'm assuming that you're talking about the minimum supply temperature and not freeze. So we'll address it with minimum supply temperature. That is whatever the minimum supply the chiller that you are serving can handle. If the chiller can handle 50 to 55 degrees, then the minimum supply temperature is 50 to 55 degrees, whatever the number is. Every chiller's got a number, so just ask the manufacturer for it. Can this VPS system be used with thermal energy storage tanks? I don't know of any reason why not, though I haven't personally been involved with the project yet. Okay? I really don't see any reason why not. How would you optimize control VFD condenser water pump in the VPF systems? How to balance flow over chillers if they have, oh, we did that one, okay. What is the best cooling tower delta temperature which should be obtained according to your experience? I assume you're talking about the range across the tower? I wouldn't say there's necessarily that so much as you may be really talking more about the approach. What is the best approach? If I start with a 78-degree wet bulb and I have an 85-degree condenser water, that's a 7-degree approach. What's the best approach? Well, that sort of depends upon the energy of the chiller versus how much you can slow the fan down on the tower. Because when you lower airflow in a tower, the approach increases. And that's the reason why we use airflow to maintain minimum condenser water temperature. When you reduce water flow, the approach improves or gets smaller until you reach the point where there's dry spots in the fill, which is why we limit it to about 80% flow. Unless you've got weir dams, or if you've got double spray header, then you really want to stick to around that 80% point and honor what the tower manufacturers don't want you to do, so to speak. What else do we have?
Roy, I think we have time for one more question. And then we need to wrap it up. The last question is, what benefit do we get by flooding the condenser?
What benefit do we get by flooding the condenser? Flooding it with what? Water or refrigerant?
If the attendee is still online, maybe you can clarify. Water. What is the benefit by flooding the condenser with water?
Maybe he means increasing the GPM. Instead of going down in GPM, go up. When you go up in GPM, if that's the question, when you go up in GPM, you actually lower the head on the chiller because, again, through the condenser, load is equal to flow times delta T. By changing the flow and make it faster, it didn't change the load. All it did was change the delta T across it. And what's entering is still the same number, whatever it is, but the leaving goes down, which reduces the head on the chiller, so you save energy on the chiller, but you may be experiencing greater energy on the pump. All right, so you kind of got to balance those two. I hope I got, is that the last question we can handle? Laxmi, are we all right now, or are we done?
I think we're done, Roy.
Okay.
We've kind of reached our time.
All right. Well, I appreciate everybody's time, and I hope I answered the questions. It's difficult when I can't hear you come back with a quick follow-up question, as to whether I hit the right thing or not, or more clarification. That's a little tough. But I hope you enjoyed the session, and will join us next time on, I guess it's December, right?
Yes,
December 6th.
December 6th.
All right. For the next one.
Yes.
Okay, well, thank you very much.
Bye-bye.